Okay, we continue in section 7.4. Let me share you with the slides again. We were talking about Hadamard matrices for generating the signal waveforms. So this is a multi-dimensional signal waveform. As you can see and compare this matrix, Hadamard matrix. The Hadamard matrix has a property that the inner product of its row is 0. As you can see, 0 into 0, 0, 1 into 0 is 0. So the waveforms can be plotted like this. Um, so we have two set of signals, S1 and S2. So this is 0 and 0. This is 0 and 1. So you can generate signal waveforms using the Hadamard matrices, which has the orthogonal row vectors. So in previous case, we have a data set consisting only of 1 bit, 0 or 1. To encode a 2-bit data set, we extend the foregoing set both horizontally and vertically, creating the matrix H2. So in this case, we want to transmit 0, 0, 0, 1, 1, 0, and 1, 1. So this is our data set. So for this 0, 0, we have this row, and then for 0, 1 we have the 0, 1, 0, 1. For 1, 0 we have 0, 0, 1, 1, and for 1, 1 we have 0, 1 and 1, 0. How this is generated? So if you look at this, uh, we have we have this H1 put over here, H1 again, H1 again, and then H1 complement. So this matrix is the complement of H1. So complement, how it becomes the complement? So since this is H1, so 0 becomes 1, 0 becomes 1, 0 becomes 1, and 1 becomes 0. So this is the complement. So this is again the orthogonal code word set using the Hadamard matrix. This is called Hadamard matrix. The lower right quadrant is the complement of the prior code word set, the lower right quadrant. So this quadrant is the complement of the prior code word set. So now we can transmit two bits at a time. The corresponding waveform look like this. So we have now four signals, S1, S2, S3, and S4. How these waveforms are generated? These waveforms can be generated using Hadamard matrix. So take the first row, 0, 0, 0, 0. So you will have this thing. So since there are four bits, so we have taken time as 100 seconds. So this is an assumption. You can change this number, but for 0, that means for every 25 seconds we have 0, again 0, 0, and 0. So in the second row we have 0, 1, 0, 1. So 0, 1, 0, 1. So again, the time interval, as you can see, is 25 seconds, then 50 seconds, 75 seconds, and 100 seconds. In the next case, we have 0, 0, and 1, 1. In the fourth row, we have 0, 1, 1, and 0. So this waveform is generated from the Hadamard matrix. So this is a very efficient way of generating multidimensional signal waveforms, and we can generate higher order Hadamard matrices as well. So in general, we can construct a code word set HK by taking of dimension. So its dimension will be 2K into 2K. Okay. So if we are sending 2 bits, that means we have a 4 by 4 matrix. K is the number of bits. K is the data. K is basically data set from HK minus 1 matrix. So you should have this matrix before you can generate HK. So HK minus 1 should be available to generate HK. So this is the size of 2K cross 2K is the size of the Hadamard matrix. Each pair of words in each code word set, H1, H2, or HK has as many digit agreements as disagreements. Hence, each of the set is orthogonal. Then we have a next code which is called bi-orthogonal code. The bi-orthogonal signal set of m total signals or code words can be obtained from an orthogonal set of m by 2 signals by augmenting it with the negative of each signal as follows. Okay. So in this case, we have bi-orthogonal uh, matrix, and it consists of hk minus 1 and the complement of hk minus 1. So now if we want to transmit 3-bit data set, so that can be transformed into bi-orthogonal code word set as follows. So data set now has 8 entries, 0, 0 up to 1, 1. So we have 8 entries, 8 data elements or data sets. Then again we have 8 entries over here. So this is hk minus 1. Suppose we have this generated from the previous case 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. So we had generated this. This was available. This will be the complement of it. So the first 4 by 4 matrix, this is, yes, it is a 4 by 4 matrix. So this is its complement. So you can see the 0 becomes 1, this 0 becomes 1, so this 1 becomes 0, 0 becomes 1. So following this structure hk minus 1 and the complement of hk minus 1. So again we can generate signal waveform using this bk matrix, and it is k is 3 since we are taking 3 bits at a time. So taking the first row, looking at the first row, this is all 0. Okay, so he has not shown the waveform. You can easily generate the signal waveforms. So another way is generating the another orthogonal signal waveforms are non-overlapping in time. Non-overlapping in time usually comes in the pulse position modulation (PPM) as follows: the digital information that is transmitted is conveyed by the time interval in which the signal pulse occupies. So this type of signaling is usually called the pulse positions. As you can see, all these signals are non-overlapping, so they occupy different time slots. So if total time is t and we want to generate 4 signals, then the time is for each signal is t by 4. So t by 4 up to t by 2, then t by 2 to 3t by 4, and then 3t by 4 to t. So this is m equal to 4 ppm. So we are talking about multidimensional signaling, signal waveforms. So in this case, the m baseband signal waveform may be expressed like this. So Sm is our baseband signal. So these are shifted pulses of amplitude A. So this is the shift m minus 1t over m, where m starts from 1 to m. So the time for each baseband starts from the previous m minus 1 to next m minus 1t over m, and mt over m, where g of t is a signal pulse of duration t by m, up and up arbitrary shape. The ppm signal have the same energy. You can generate the signal energy by using this expression. We have already discussed it, and it's m basis function. Since it is an m-dimensional signal, so we have m ppm or m basis functions or m array signaling. So this will require m basis function of this structure. So this is the amplitude for this orthogonal basis function during this time interval. Otherwise, it is 0. So the m array ppm can be signal waveforms are represented geometrically. Geometrically means that we want to generate their vectors. So if we have S1 up to Sm signals, so each will be occupying different, as you can see, so Es energy under the root will be coming on the diagonal. So these are all orthogonal signal waveforms. The M signal vectors are mutually equidistant. So if you take the distance from S1 and S2 or S2 to S3, this becomes this minus this plus this. The difference will be equal to, so this minus 0, this minus 0, and then taking the square. So this will become under root 2 times Es. So this is the minimum distance between any two signal points. So its band pass signal can be generated by multiplying Sm with the carrier signal. Simply cosine 2 pi fct and multiply it with Sm. So energy of this U signal, which is the band pass signal, is Es over 2. The most popular orthogonal band pass signals are the carrier frequency modulation. Okay, frequency modulation to they achieve orthogonality in the frequency domain. The simplest form is frequency shift keying. So now we will talk about frequency shift keying. It's very simple. So in frequency shift keying, binary frequency shift keying, we imply two different frequencies, say F1 and F2. F2 is F1 plus delta F. So these are the two frequencies. So in the case of BFSK, binary FSK, okay, to transmit a binary information sequence. Thus, the two signal waveform will be expressed as, so this is the first case where the amplitude of this is 2 times EB over TB under the root cosine 2 pi F1T. The duration is 0 to TB. TB is any time interval. So as you can see, this is a signal of one frequency, F1. This is signal of another frequency, F2. Okay. So F1 and F2 are related by this expression, F1 plus some shift in the frequency. So let us take an example of frequency shift keying. So suppose F2 is 2 times F1. Okay. So we have already decided that F1 will be transmitting 0 and 1 will be transmitted using this frequency. So if we want to transmit a sequence 0, 0, 1, 1, 0, 1, 1, so we have for this 0, we will use first frequency. So this is the, for each t, 0 to t, we have, if this is the signal for F1, then again 0. So this is F1 again, then we have 1. Okay, so F1, for 1 we have 2 times F1. So this is the double frequency. For each time interval 2t to 3t, we have now 2 cycles. Again, we have 2 cycles in 3t to 4t for this segment, 1, 1. Then we have 0 over here, and again we have 1, 1. From 5t to 6t and 6t to 70, we have transmitted to 1, 1. So M-array FSK is used to transmit a block of k equal to log 2m bits per signal waveform. So for each signal waveform, we are now using k bits. So if we have k bits, then we can use the band pass signal like this, cosine 2 pi fct plus 2 pi m delta f times t. So in this case, we are using m, so we can generate as many band pass signal as is the value of the m. So this small m is equal to 0 up to m minus 1. Okay, so we can generate M-array FSK signal waveforms using this expression. This is the band pass signal, and because it is using a carrier frequency Fc. So in this case, Es is equal to K times Eb is the energy symbol, energy per symbol. T is equal to K times Tb. Okay, so the bit duration, the bit symbol interval is now T, which is K times Tb. Is the symbol interval, and delta F is the frequency separation between successive frequencies. So delta F is Fm minus Fm minus 1, okay, where Fm is equal to Fc plus m, m times delta F. So this is the frequency deviation, m times delta F. In order to guarantee orthogonality between FSK signal, the correlation coefficients of FSK signal should be 0. Okay, so this is the correlation signal. The correlation between any two band pass signal UM and UM, it should be 0 at some point. So if you can see that taking this one, this is the correlation coefficient expression gamma mn. So we have UM signal and then UN signal. So if we want this signal to be this is the final expression for correlation coefficient. So if we want this to be 0, so delta F should be multiple of 1 by 2t. Okay, so delta F should be 1 by 2t. So these are the points 0, 0. So the difference is 0.5 over t. Okay, so he has normalized it over here. So you can take delta F equal to 1 by 2t. Okay, or if since this is normalized because delta F into t, so we are only considering the spacing as 0.5. So you can see that this is 0.5, then again 0 at 1, then 0 at 1.5, 2 at 2 it is again 0. So correlation coefficient. So the spacing should be such that this condition is satisfied. Delta F is a multiple of 1 by 2t. Then another multi-dimensional signaling is called MSK, or minimum shift keying. So we can also read this. I will skip this because it is a little bit involved. So we will not consider MSK, but this is a very important uh, modulation scheme, and it is a multi-dimensional signaling scheme. So its variant GMSK, or Gaussian minimum shift keying signal, is used in wireless systems such as GSM. So this is the structure of the modulator that is used. So in this case, the only thing we do here is differential coding, and then we use two oscillators. So this is MSK modulator. You can read it by yourself. Again, we are using orthogonal signals, and MSK is a continuous phase modulation scheme. Okay, next we come to bi-orthogonal signal waveforms. Okay, so previously we were talking about only orthogonal signal waveforms, and orthogonal signal waveform can be generated using Hadamard code words or Hadamard matrices. And Hadamard matrices are very important. They are used in its variant Walsh Hadamard matrix is used in CDMA systems. So again, we come back to our syllabus. Let me show you the syllabus. So we have now so if we look into our syllabus for midterm, so we are actually covering this chapter 7, and we have now covered section 7.1, 7.2. 7.2 was for two-dimensional signaling. Then we have covered section 7.3, 7.3. Then we covered this multi-dimensional signaling. In this case, we have covered orthogonal signal waveforms, baseband signals, and then we covered the frequency shift keying. As you can see, we have covered frequency shift keying. Okay, so now we will talk about bi-orthogonal signal waveforms. So this is section 7.4.2. So we will first start from the baseband signals. So baseband signals can be generated similarly as in the multidimensional signaling we discussed previously. So in this case, the only difference is that we are taking two sets of signal. The first set is from S1, S2 up to Sm by 2. So they all have equal energies on their diagonal elements. So ES, ES, and ES under the roots. And then we take another set which starts from Sm by 2 plus 1 up to Sm. So we are dividing the whole uh, signal set from 1 to m into two sets. So we divide it into two sets up to S1 to Sm by 2, and then from Sm by 2 plus 1 up to Sm. So you see that this is just the negative of this first one. So negative ES under the root and up to Sm signal. So this is called bi-orthogonal signaling set. Okay. So you first read this stuff baseband signal, and so the other set, the first set is positive, and the other and their negative is minus Si. So we want to generate signaling or signal set from Si, which goes from I equal to 1 up to m by 2, and then their negative, which starts for the m by 2 plus 1 up to m. The figure 7.15 illustrates the signal constellation for M equal to 4 bi-orthogonal signal. So this scheme is called bi-orthogonal signaling scheme. 7.15, where is 7.15? So it is given previously 7.15. So this is the bi-orthogonal signaling scheme for M equal to 4. You can see that S1 and then it has minus S1, S2 and then minus S2. So they are orthogonal. So this scheme is for M is equal to 4 bi-orthogonal signals. So similarly, we can create its band pass signals by simply multiplying the baseband signal with the carrier frequency cosine 2 pi fct. So SMs are no different. So the geometric representation of band pass signal is identical to that of the corresponding baseband signal, where the energy of the band pass signal waveform is one of that of the corresponding baseband signal. Okay, the last topic is simplex signal waveforms. So in this case, we this is our last section 7.43. How to generate simplex signal waveform. Another set of M signal waveform that can be constructed from M orthogonal signals is obtained by subtracting the average of M orthogonal signals from each of the orthogonal signal waveforms. So this is the average of M orthogonal signals, and this is subtracted from Sm. So we generate a new signal waveform, Sm slash T. So this take the previous Sm and subtract k equal to 1 to M signals, sum them, and then divide by M. So this is the average. Okay. So the M signal waveform that results are called simplex signal waveform. Thus, if we have M orthogonal baseband signal waveform Sm, the simplex signal waveform denoted by are constructed as. Then it follows from problem 7.7, the energy of these signals. So energy of these signal is simply taking the square of this signal. So they have already calculated it. You can go to problem 7.7, its solution. So you will see that it is equal to 1 minus 1 over m times ES. And the corresponding uh, signals are orthogonal. So the Sm bar and Sn bar T dt is equal to minus 1 over m minus 1 EFS, where m is not equal to n. The ES is the energy of the orthogonal signal, and ES bar is the energy of each of the signal in the simplex signal set. So the geometric representation, it looks like this. So now we have vector. This vector is subtracted from the average of the vectors, m orthogonal vectors. So this is the geometric representation of the simplex signals. So, similarly, its correlation coefficient is -1 over m minus 1. Hence, all the signals have the same pairwise correlation. And figure 7.27 illustrates a set of m equal to 4 simplex signals. Figure 7.27. So, signal constellation for m is equal to 4 simplex signals. So, this S1, then this is S2, S3, and S4. It looks like a tetrahedron type structure. Okay. So next we move, after simplex signals, we'll move to binary coded signal waveform. This is also very simple. Signal waveforms for translating digital information may also be constructed from a set of m binary code words of the form. CM is equal to CM1, CM2 up to CMN. So this is a code word. Okay. So CMJ is equal to 0 or 1 for all m and j. It can, so this number can be 0 or 1 or something like that. N is called the block length or dimension of the binary coded words, binary code words. Given m code words, we can construct m signal waveform. So using these code words, we can generate m signal waveform by mapping a code bit CMJ equal to 1 into a pulse GT of dimension T by n, and a code bit CMJ equal to 0 into negative pulse minus G of T. Okay. If we want to transmit a 1, so we have to use a pulse GT of positive of duration T by n, and a code if we want to transmit 0 into, then we take a negative of that thing. So let us see this. So given the code words C1, C2, C3, C4, construct a set of m is equal to 4 signal waveforms as described above using rectangular pulse of the GT. Okay. So if you look at this, so we have 4 ones now. So T by n, n will be so n will be 5 in this case because we have 5 elements. So we will divide time interval t into 5 different time intervals. So t by 5. So first is t by 5, 2t by 5, 3t by 5, 4t by 5, and then 5t by 5. So mapping this code vector 1, 1, 1, 1, 0, so we can generate this signal. So 1, 1, 1, 1, and then 0. So this is 1. This is for second code word 1, 1, 0, 0, 1. 1, 1, 0, 0, 1. So this is very straightforward. So you can use this to this code word to generate signal waveforms. Okay, similarly for S3 and S4. So m is equal to 4 in this case, and dimension n is equal to 5 constructed from the 4 code words given in example 7.41. So let us consider the geometric representation of set of m signal waveform generated from a set of m binary code words. So these are the binary code words, and these are the corresponding m signal waveforms are of dimension n and are represented geometrically in vector form. So each SM1 is equal to either positive or negative. So E energy ES divided by n under the root plus minus, so positive or negative depending upon the signal waveform shape. So in this case, the correlation coefficient is n minus 2 divided by n, and then the corresponding Euclidean distance is 2 times Es by n under the root. So we have n is equal to 4. So we have 2 orthogonal sets. If we have n equal to 3, then we have 8 points. Okay. So they are all orthogonal to each other. So this is our S1, S2, S3, S4, S5, 6, 7, and 8. The signal space diagram for signal generated from the binary codes. So we have now 3 orthogonal basis functions, phi 1, phi 2, and phi 3. So we have covered section 7.4, which is for multidimensional signaling. So the key concept is that you map the bits to signals using different techniques. So we discussed frequency shift keying, we discussed Hadamard matrices, binary coded words to generate the signal sets. And then we also found their Euclidean minimum distances, correlation coefficients, and then their constellation diagrams. So I will stop it over here and I will share these videos with you. And the next important topic is now we are ready to go towards optimum receiver for digitally modulated signals in additive white Gaussian noise. Optimum receiver for digitally modulated. So this will be our next topic. So uh, we will discuss it in our next video. Until that time, okay. Thank you very much for watching this video and Allah Hafiz. Assalamu alaikum.